Alright guys, so the main point of the 4 is that we are going to be able to say that if I have a function set up such as this, that f of x will be the derivative of a prime. So now if it says a of x is equal to that integral where f is that function, then that function, if set up from a constant to a variable, is equal to a prime. So now I'm looking at the graph of the derivative and then making calls from there. So we're just going to go back and do the same thing that we've done with derivatives, but as it applies to a function that's defined as an integral. So for example, if this is a prime, on the open interval from -7 to 7, a prime is equal to 0 at -1, 1, and 5. Because that's where that graph, a prime, is equal to 0. Where does a prime not exist? Well, this graph exists everywhere, so that would be nowhere. It does not exist nowhere. Where is a continuous? Well, if you remember, differentiability implies continuity. So if the function is differentiable everywhere, which it is because the derivative exists everywhere, then this is continuous everywhere on that closed interval from -7 to 7. Where does the second derivative equal 0? Well, that's going to be wherever this graph has a slope of 0. And this graph has a slope of 0 from -7 to -3. And I'm going to leave that open because I'm on an open interval, and at -3 I have a corner. So when I get to E, and it says from -7 to 7 open, where does the second derivative not exist? That's going to be at any corner, cusp, or vertical tangent on this graph, which would be x equals -3, x equals 0, and x equals 3. Where is a increasing? Why, wherever a prime is positive. So we are increasing from, in brackets, -7 to -1, and again from 1 to 5. Why? Because a prime is greater than 0, or equal to, excuse me. A prime is greater than or equal to 0. Where does a, from open interval -7 to 7, have relative mins? Well, relative minimums occur where the first derivative changes from a negative to a positive. So that's going to be at x equals 1. And you're going to say, because a prime changes, and I'm going to abbreviate because of lack of space, from negative to positive. Where does a have relative maximums? Wherever a prime changes from positive to negative. So that would be at x equals -1 and x equals 5. And my justification would basically be the same, because a prime changes from positive to negative. And again, I don't want you abbreviating. I just only have that much space, so please make sure you're spelling out the entire thing. Where does on A, on the closed interval from -7 to 7, have inflection points? Wherever this graph has a max or a min, which would be at x equals 0 and x equals 3, because this graph is changing from increasing to decreasing, or vice versa. So a double prime would be changing from positive to negative, or vice versa. So you would say where a prime has max and mins, or the second derivative would change signs, equals 0 does not exist and changes signs. And then finally J. Now this one's going to be a long one. It looks easy, but it's not. On the interval closed from -7 to 7, where does A achieve its max and min values? Well, guess what, guys? It's on a closed interval. So therefore, EVT applies. And I am going to have to check any place where my first derivative is equal to 0, does not exist, and at the end points. So I'm going to create a table, and I'm going to do it down here just so you can see what I'm doing. I'm going to substitute in x, and then my output is just the a value. But now watch what we're going to have to do. I need to substitute in -3, -1, 1, 5, and 7 to evaluate where I have maxes and mins. And when I evaluate A, I'm going to actually have to take the area from 0 to -3, this area from 0 to -1, this area from 0 to 1, from 0 to 5, and from 0 to 7, because my input now refers to that B value. So very quickly, and you can spend time on this, if I'm going to find the area underneath the curve from 0 to -3, I'm going to use my slopes here. These two would cancel out, and then I have 1, 0 to -3, I have 1.5, so that'd be 3/2. But negative, because I went to the left and up. If I want to go to -1, from 0 to -1, that would be actually a positive 1/2, because I was changing from positive to negative here, so I should be looking at a maximum, but I also went from 0 to -1, so I went to the left and down, giving me a positive value. So likewise at 1, from 0 to 1, I'm going to the right and down, so that value here would be a -1/2. From 0 to 5, I have -1/2, positive 1/2, which will cancel each other out, plus 1, 2, 3.5. So that's equal to 7/2 there. And then from 7/2, I'm going to subtract, because I'm going to the right and down, another 2. So that'd be 7/2 minus 2, which would be equal to 3/2. Notice where my max occurred at x equals 5, because my first derivative changed from a positive to negative, and my minimum ended up occurring at x equals, well, at x equals -1/2, but my absolute minimum occurred at an endpoint at x equals -3/2. So our justification statement is going to say EBT applies, A was closed and continuous. We're going to make a table showing all those values of the area underneath that curve, and then answer with the max and min values. So the max value was 7/2, and the minimum value was -3/2. I'm checking zeros, and I'm checking endpoints. We're going to try it again with number 8. Just come back.